Welcome. We will now continue with group representation of finite groups. And we're still in group characters and we're in the part 3 of it. So we continue by considering this theorem. We would not be proving it in this video. It says let AX be an arbitrary representation of degree n and not necessarily irreducible. And then we have phi of x, and it is a character of ax. Then you can as well write the phi of x inverse to be the phi bar of x. Okay, so where the bar denotes the complex conjugate. So we just need you to know this. I will be using it in one of the questions or proofs as we continue in the video. So sorry, there's just a single bracket there, not two of it. Okay. Now, proposition 2.2 in your lecture notes says show that in the construction of the induced representation. So we have a induced representation matrix. If you remember, where we had the diagonals of this form, Ti inverse. If you remember, in the previous videos we had something like that. Okay, well, so it's saying that in constructing this representation, induced representation of AX, the choice of your particular transverse does not materially affect the result. So what result? So you understand the choice and the result is actually the sum of your diagonals. So that's the induced character. It doesn't affect it. That's what we mean there. So I should have stated what result I meant. Okay, but let's see. So the solution is this. Now, in constructing our induced representation AX, if you recall, we had a subgroup H, if you recall, and then we saw that H can be expressed as a union of the coset in terms of the subgroup H, right? And the Ti's, that's T1 to Tn, are right transversals, so those are our transversals. Okay, and we saw that the induced character will be the trace of AX, which is written as you can see here. Okay, now once we have this knowledge, this is the result I was saying that the question was saying it would not materially affect it. So we want to show that if we choose another transversal, you recall now, I had earlier said that these are transversal for the induced matrix. So if we matrix representation, so if we choose another transverse, we want to show that it will not affect this final solution for the character of the induced representation. So we're choosing this new transverse, and it will be so on the grounds that it's from. You remember that we had Ti, so you can see the T here. We pick Ui from our H. Remember, H is the subgroup, right, of group G. Now, so if our Si, our new transverse, is the Si, as you can see there. So if S can be written this way, if we want to write it to be our new terms in our induced matrix, it means that it's going to take this form, right? So if wherever we see Si and Si inverse, just substitute our Ui, Ti, as you can see, substituted right there. Now this term remains as it is, and the X still remains the same. But remember what happens when you have Ui, Ti inverse, it becomes Ti inverse, Ui inverse. And associativity allows us to have what you see in the middle there, and it's almost like the term up here, only that this is for, so only that the term up here is when we have our transversals to be this. Now when we have the transversals to be this, we're getting that there will be a kind of relationship in terms of the Ti's, as you can see right here. Okay, so let's see what happens. Now we want to verify that this sum, this one with the SI's now, because that's our new transverse, will be same as this. That's our target. We want to show that it doesn't materially affect it. Okay, but now we know that from the induced character representation that this phi of x, whenever you pick phi of x goes to 0 whenever x is not in a subgroup of our group G, right? The H itself. So once it's not there, the character of x at the point x is 0. So all we need to do, we want to check if this sum now, as you sum through each of the terms, what happens to phi x ix si inverse, whether it will be the same as this. So all we need to do is check each of the terms as we go from 1 all the way to n. We check what happens when I is 1 all. But if we're going to sit down checking them one by one, that will take a long time. But if we use this condition here, knowing that we're working with the induced matrix, remember? Induced representation matrix. That's what brought us this way. So we just consider if this value here is in H and when it is not in H. So that's why we said we have two cases to consider. And the first case we're going to consider is when this term SI inverse lies in H. So what happens if SI inverse lies in H? Automatically it means that our equality, if you remember, we had said that SI xi is same as this, and we're able to simplify it to get this down here. Okay, so SI xi is this. So wherever I see this, I'll put this. So now, so we are trying to check what happens if it SI inverse lies in H. What will happen? So if it lies in H, it means the entire term which we got earlier lies in H, meaning that this term in the middle lies in H, right? That's how I got this one here. So if that is the case, it means that whenever I take the phi of SI inverse, it will be the same as phi of TI inverse. Why? Because they are conjugate elements. That's what makes it possible, and that makes them a class function, as I explained earlier in class. Okay, so it means whenever we have this relationship SI inverse in H, this function, our character, will be the same with that of TI inverse. Okay, so we settled terms whenever SI is in H. So the next thing we need to consider is when it isn't in it, right? Because we already said there are two cases. So what happens when it isn't in it? So case 2, if SI inverse isn't in H, it means this entire term wouldn't be in H, right? Which means that this term isn't in H. And we already know from the previous slide that wherever x is not in H, the character goes to 0. So you can see here. So let's go back now. So we've seen that if SI inverse isn't in H, then all of this term wouldn't be in H. Therefore, TI inverse wouldn't be in H. Hence, these two terms are the same, and guess what? They are all equal to 0. Okay, so it trivially satisfies both sides because they go to 0. Whenever SI inverse lies in H, this is equal to this, and you get the value 0 for those terms. So while summing, so if you combine the two cases for the terms when SI is in H and when when XI wasn't in H and case is in H, you combine all the terms together, summing from I to N, you get equality. Why? Because you will only be left with terms that are not equal to 0. And the terms not equal to 0 will just be this term and this term as you sum. Hence, there is no change. This term equal to this term. So it doesn't materially affect our final results. Okay? So that's also the proof of this particular problem. Now, I want us to note something. That this SI, we were able to write it in this form, right? So the character of the induced matrix or representation can be written as this, and hence like this, right? Because we're able to write it because it doesn't really affect it, right? So all we've just done is to sum over U in H, wherever the U is in H, and set Y to be equal to the UITI, and we have a new way of writing the character representation, sorry, the character for an induced matrix, and it takes this form. Note, we're having H because whenever X is not in H, all the character goes to what? 0. So we don't count the terms. It's only those that head into 0. So, and we use the order of our group H, of our subgroup H. So that's why if you note, the terms are terms in G. However, because terms that are not in H goes to 0, we will just get H of them. Okay, so you can write it in this way. Okay, so that's a new way of writing our character for the induced representation, noting that no matter the transverse you use, it doesn't materially affect the character of the induced representation. So with that, thank you.